Hey guys, I'm back again. Let me continue. Storage for the new node is fetched by a routine TLOC, which is an adapt adaptation, which is an adaptation of the alloc we wrote earlier. It returns a pointer to a free space suitable for holding a tree node. We will discuss this more in a moment. The new word is copied to a hidden place for to save. The count is initialized, and the two children are made null. This part of the code is executed only at the edge of the tree. When a new node is being added, we have wisely for a production program, emptied error checking on the values returned by save and tlog. Tree print prints the tree in left subtree order. At each node, it prints the left subtree, all the words less than this word, then the word itself, then the right subtree, all the words greater. If you feel shaky about recursion, draw yourself a tree and print it with tree print. It's one of the cleanest recursive routines you can find. A practical note: if the tree becomes unbalanced because the words don't arrive in random order, the running time of the program can grow too fast. In the worst case, if the words are already in order, this program does an expensive simulation of linear search. There are generalizations of the binary tree, notably two middle-score 3 trees and AVL trees, which do not suffer from this worst-case behavior, but we will not describe them here. Before we leave this example, it is also worthy a brief digression on a problem related to storage allocators. Clearly, it's desirable that there be only one storage allocator in a program, even though it allocates different kinds of objects. But if one allocator is to process requests for, say, pointers to chars and pointers to struct T nodes, two questions arise. First, how does it meet the requirement of most real machines that objects of certain types must satisfy alignment restrictions? For example, integers often must be located on even addresses. Second, what declarations can cope with the fact that a log necessarily returns different kinds of pointers? Alignment requirements can generally be satisfied easily at the cost of some wasted space, merely by ensuring that the allocator always returns a pointer that meets all alignment restrictions. For example, on the PDP-11, it is sufficient that a log always return an even pointer. Since any type of object may be stored at an even address. The only cost is a wasted character on odd length requests. Similar actions are taken on other machines, thus the implementation of a log may not be portable, but the usage is. The log of Chapter 5 does not guarantee any particular alignment. In Chapter 8, we will show how to do the job right. The question of the type declaration for a log is a fixing one for any language that takes its type checking seriously. In C, the best procedure is to declare that a log returns a pointer to char, then explicitly calls the pointer into the desired type with a case. That is, if P is declared as char asterisk P, then like this, converts it into a T0 pointer in an expression. That TLOG is written. This is more than is needed for current compilers, but represents the safest course for the future. Exercise 6, middle score 4. Write a program which reads a C program and prints in alphabetic order each group of variable names which are identical in the first 7 characters but different somewhere thereafter. Make sure that 7 is a parameter. Exercise 6, middle score 5. Write a basic cross-referencer, a program which prints a list of all words in a document. And for each word, a list of the line numbers on which it occurs. Exercise 6, middle score 6. Write a program which prints the distinct words in its input sorted into a decreasing order of frequency of occurrence. Precede each word by its count. 6.6 Table Lookup. In this section, we will write the inners of a table lookup package as an illustration of more aspects of structures. This code is typical of what might be found in the simple table management routines of a macro processor or a compiler. For example, consider the C hash define statement when a line like hash define yes1 is encountered, the name yes and the replacement text 1 are stored in a table. Later, when the name yes appears in a statement like inward equal yes, it must be replaced by 1. There are 2 major routines that manipulate the names and replacement text. Install parenthesis s comma t records the name s and the replacement text t in a table. S and t are just character strings. Lookup parenthesis s searches for s in the table and returns a pointer to the place where it was found, or null, even if it wasn't there. The algorithm used is a hash search. The incoming name is converted into a small positive integer, which is then used to index into an array of pointers. An array element pointers to the beginning of a chain of blocks describing names that have that hash value. It is null if no names have hashed to that value. A block in the chain is a structure containing pointers to the name, the replacement text, and the next block in the chain, a new next pointer marks the end of the chain. Pointer array is just the hashing function which is used by both lookup and install. Simply adds up the character values in the string and forms the remainder modulo the array size. This is not the best possible algorithm, but it has the merit, but it has the merit of extreme simplicity. The hashing process produces a starting index in the array hash tab. If the string is to be found anywhere, it will be in the chain of blocks beginning there. The search is performed by lookup. If lookup finds the entry already present, it returns a pointer to it. If not, it returns null. Install uses lookup to determining whether the name being installed is already present. If so, the new definition must supersede the old one. Otherwise, a completely new entry is created. Install returns null. If for any reason there is no room for a new entry. Receive merely copies the string given by its argument into a safe place, obtained by a call on a lock. We showed the code in Chapter 5, since calls to unlock and free may occur in any order. And since alignment matters, the simple version of a lock in Chapter 5 is not adequate here. Seeing Chapter 7 and 8. Exercise 6, middle score 7, write a routine which will remove a name and definition from the table maintained by lookup and install. Exercise 6, middle score 8, implement a simple version of the hash-defined processor suitable for use with C programs based on the routines of this section. You may also find Getch and Ngetch helpful. 6.7 Views. When the storage space is at a premium, it may be necessary to pack several objects into a single machine word. One especially common use is a set of single bit flags in applications like compiler symbol tables. Externally imposed data formats, such as interfaces to hardware devices, also often require their ability to add pieces of a word. Imagine a fragment of a compiler that manipulates a symbol table. Each identifier in a program has certain information associated with it. For example, whether or not it is a keyword, whether or not it is external or static, and so on. The most compact way to encode such information is a set of 1-bit flags in a single char or int. The usual way this is done is to define a set of masks corresponding to the relevant bit positions, as in, the numbers must be powers of 2. Then, accessing the bits becomes a matter of bit bit fitting, with the shifting, masking, and complementing operators, which were described in chapter 2. Certain idioms appear frequently. Terms on the external and static bits in flags, while terms them off, and like this is true if both bits are off. Although these idioms are readily mastered, as an alternative, C offers the capability of defining and accessing fields within a word directly rather than by bitwise logical operators. A field is a set of adjacent bits within a single int. The syntax of field definition and access is based on structures. For example, the symbol table hash defined as above could be replaced by the definition of 3 fields. That defines a variable called a flags that contains 3 1-bit fields. The number following the column represents the field width in bits. The fields are declared unsigned to emphasize that there really are unsigned quantities. Individual fields are referenced as flags. Point is underscore keyword, etc. Just like other structure members, fields behave like small unsigned integers and may participate in arithmetic expressions just like other integers. Thus, the previous examples may be written more naturally as to return the bits on, to turn them off, to test them. A field may not overlap an int boundary if the width would cause this to happen. The field is aligned at the next int boundary. Fields need not be named. Unnamed fields, a column and a width only, are used for padding. The special width 0 may be used to force alignment at the next int boundary. There are a number of cafes that apply to fields. Perhaps most significant fields are assigned left to right on some machines and right to left on others, reflecting the nature of different hardware. This means that although fields are quite useful for maintaining internally defined data structures, the question of which end comes first has to be carefully considered when picking apart externally defined data. Other restrictions to bear in mind: fields are unsigned. They may be stored only in int or equivalently unsigned. They are not arrays. They do not have addresses, so the ampersand operator cannot be applied to them. 6.8 Unions. A union is a variable which may hold at different times objects of different types and sizes, with the compiler keeping track of size and alignment requirements. Unions provide a way to manipulate different kinds of data in a single area of storage without embedding any machine-dependent information in the program. As an example, again, from a compiler symbol table, suppose that constants may be int, floats, or character pointers. The value of a particular constant must be stored in a variable of the proper type. Yet it is most convenient for table management if the value occupies the same amount of storage and is stored in the same place regardless of its type. This is the purpose of a union, to provide a single variable which can legitimately hold any one of several types. As with fields, the syntax is based on structures. The variable uval will be large enough to hold the largest of three types, regardless of the machine it is compiled on. The code is independent of head or characteristics. Any of these types may be assigned to uval and then used in expressions, so long as the usage is consistent. The type retrieved must be the type most recently stored. It is the responsibility of the programmer to keep track of what type is currently stored in the union. The results are machine dependent. If something is stored as one type and extracted as another, syntactically, members of a union are accessed as, or just as for structures, if the variable utype is used to keep track of the current type stored in uval. Then one might see code such as like this. Unions may occur within structures and arrays, and vice versa. This notation for accessing a member of a union in a structure, or vice versa, is identical to that for nested structures. For example, in the structure array defined for the variable ival is referred to as like this, and the first character of the string pval by like this. In effect, a union is a structure in which all members have offset 0. The structure is big enough to hold the widest member, and the alignment is appropriate for all of the types in the union. As with structures, the only operations currently permitted on unions are accessing a member and taking the address. Unions may not be assigned to passed to functions or returned by functions. Pointers to unions can be used in a manner identical to pointers to structures. The storage allocator in Chapter 8 shows how a union can be used to force a variable to be aligned on a particular kind of storage boundary. 6.9 TypeDiff. C provides a facility called TypeDiff for creating new data type names. For example, the declaration TypeDiff int length makes the name length a synonym for int. The type length can be used in declarations, kits, etc. in exactly the same ways that the type int can be similarly the declaration makes string a synonym for char, asterisk, or character pointer, which may then be used in declarations like. Notice that the type being declared in a type div appears in the position of a variable name, not right after the word type div. Syntactically, type div is like the storage classes, extern, static, etc. We have also used uppercase letters to emphasize the names. As a more complicated example, we could make type divs for the three nodes shown earlier in this chapter. This creates two new type keywords called tree node structure and tree PTR, a pointer to this structure. Then the routine talog could become like this. It must be emphasized that a type div declaration does not create a new type in any sense. It merely adds a new name for some existing type. Nor are there any new subject variables declared this way have exactly the same properties as variables whose declarations are spelled out explicitly. In fact, type div is like hash define, except that since it is interpreted by the compiler, it can cope with textual substitutions that are beyond the capabilities of the C macro preprocessor. For example, like this, create is the type PFI, for example, for pointer to function returning int, which can be used in context like in the sword program of chapter 5. There are two main reasons for using type div declarations. The first is to parameterize a program against portability problems. If type divs are used for data types which may be machine dependent, only the type div is need change when the program is moved. One common situation is to use type div names for various integer quantities, then make an appropriate set of choices of short, int, and long for each host machine. The second purpose of type div is to provide better documentation for a program. A type called tree PTR may be easier to understand than one declared only as a pointer to a complicated structure. Finally, there is always the possibility that in the future, the compiler or some other program such as Mint may make use of the information contained in type div declarations to perform some extra checking of a program. Guys, what happened? Chapter 7, Input and Output. Input and output facilities are not part of the C language. So we have de-emphasized. So we have de-emphasized. So we have de-emphasized them in our presentation thus far. Nonetheless, real programs do interact with their environment in much more complicated ways than those we have shown before. In this chapter, we will describe the standardized natural library, a set of functions designed to provide a standardized natural system for C programs. The functions are intended to present a convenient programming interface yet reflect only operations that can be provided on most modern operating systems. The routines are efficient enough that users should seldom feel the need to circumvent them for efficiency, regardless of how critical the application. Finally, the routines are meant to be portable, in the sense that they will exist in compatible compatible form on any system where C exists, and that programs which confine their system interactions to facilities provided by the standard library can be moved from one system to another essentially without change. We will not try to describe the entire ICE natural library here. We're more interested to showing the essentials of writing C programs that interact with their operating system environment. 7.1 Access to the standard library. Each source file that refers to a standard library function must contain the 9 hash include studio .h near the beginning. The file studio.h defines certain macros and variables used by the ICE natural library. Use of the angle braces. Oh, this is angle braces. Left angle brake and right angle brake instead of the usual double quotes directs the compiler to search for the file in a directory containing standard header information. On Unix, typically /user /include. Furthermore, it may be necessary when loading the program to specify the library explicitly. For example, on the PDP-11 Unix system, the command to compile a program would be load files, etc. Midscore ls, where ls indicates loading from the standard library. The character L is the letter L. I know, it's not 1, it's L. So confused. 7.2 Standard input and output, get char and pull char. The simplest input mechanism is to read a character at a time from the standard input. Generally, the user's terminal with get char parenthesis returns the next input character each time it is called. In most environments that suppose C, a file may be substituted for the terminal by using the angle break convention or less than convention. If a program prog uses get char, then the command line prog less than infile causes prog to read infile instead of the terminal. The switching of the input is done in such a way that prog itself is obvious to the change. In particular, the string less than infile is not included in the command line argument in argv. The input switching is also invisible if the input comes from another program via a pipe mechanism. The command line runs the two programs, other prog and prog, and arranges that the standard input for prog comes from the standard output of other prog. Getchar returns the value EOF when it encounters and a file on whatever input is being read. The standard library defines the symbolic constant EOF to be -1, with a hash defined in the file studio.h, but test should be written in terms of EOF, not -1, so as to be independent of the specific value. For output, putchar puts the character C on the standard output, which is also by default the terminal. The output can be directed to a file by using greater than colon. If prog uses putchar like this, we'll write the standard output onto out value instead of the terminal. On the Unix system, a pipe can also be used. Puts the standard output of prog into the standard input of the other prog. Again, prog is not aware of the redirection. Output produced by printf also finds its way to the standard output, and calls to putchar and printf may be interleaved. A surprising number of programs read only one input stream and write only one output stream. For such programs, iSnapshot with getchar, putchar, and printf may be entirely adequate, and is certainly enough to get started. This is particularly true given file redirection and a pipe facility for connecting the output of one program to the input of the next. For example, consider the program lower, which maps its input to lowercase. The functions is upper and to lower are actually macros defined in studio.h. The macro is upper tests whether its argument is an uppercase letter, returning non-zero if it is and 0 if not. The macros to lower converts an uppercase letter to lowercase, regardless of how these functions are implemented on a particular machine. Their external behavior is the same, so programs that use them are shielded from knowledge of the character set. To convert multiple files, you can use a program like the Unix Autodidactism to collect the files, and thus avoid learning how to access files from a program. CAD is presented later in this chapter. As an aside, in the standard iSnapshot library, the functions getchar and putchar can actually be macros, and thus avoid the overhead of a function called per character. We will show how this is done in chapter 8. 7.3 Formatted output printf. The two routines printf for output and scanf for input. Next section. Permit translation to and from character representations of numerical quantities. This also allows generation of interpretation of formatted lines. We have used printf informally throughout the previous chapters. Here is a more complete and precise description. Printf converts formats and prints its arguments on the standard output under control of the string control1. The control string contains two types of objects: ordinary characters, which are simply copied to the output string, and conversion specifications, each of which causes conversion and printing of the next successive argument to printf. Each conversion specification is introduced by the character % and ended by a conversation character. Between the % and the conversion character, there may be a minus sign, which specifies left adjustment of the converted argument in its field. A digit string specifying a minimum field width. The converted number will be printed in a field at least this wide and wider if necessary. If the converted argument has fewer characters than the field width, it will be padded on the left or right if the left adjustment indicator has been given. To make up the field width, the padding character is blank normally and 0 if the field width was specified with a leading 0. This 0 does not imply an octal field width. A period, which separates the field width from the next digit string. A digit string, the precision, which specifies the maximum number of characters to be printed from a string, or the number of digits to be printed to the right of the decimal point of a float or double. A length modifier L, letter L, not 1, I know, which indicates that the corresponding data item is a long rather than an int. The conversion characters and their meanings are: D, the argument is converted to decimal notation. O, the argument is converted to unsigned octal notation without a leading 0. X, the argument is converted to unsigned hexadecimal notation without a leading 0 lowercase x. U, the argument is converted to unsigned decimal notation. C, the argument is taken to be a single character. S, the argument is a string. Characters from the string are printed until a new character is reached, or until the number of characters indicated by the precision specification is exhausted. E, the argument is taken to be a float or double and converted to decimal notation of the form. What is this? Where the length of the string of n's is specified by the precision. The default precision is 6. F, the argument is taken to be a float or double and converted to decimal notation of the form, where the length of the string of n's is specified by the precision. The default precision is 6. Note that the precision does not determine the number of significant digits printed in F format. G, use %E or %F, whichever is shorter. Non-significant zeros are not printed. If the character after the % is not a conversion character, that character is printed. Thus, % may be printed by %%. Most of the format conversions are obvious and have been illustrated in earlier chapters. One exception is precision as it relates to strings. The following table shows the effect of a variety of specifications in printing Hello World. 12 characters. We have put colons around each field so you can see its extent. A warning: printf uses its first argument to decide how many arguments follow and what their types are. It will get confused and you will get nonsense answers if there are not enough arguments or if there are the wrong type. Exercise 7.7 Middle School 1. Write a program which will print after input in a sensible way. As a minimum, it should print non-graphic characters in octal or hexadecimal according to local custom, and fold long lines. 7.4 Formatted input scanf. The function scanf is the input analog of printf, providing many of the same conversion facilities in the opposite direction. Scanf reads characters from the standard input, interprets them according to the format specified in control, and stores the results in the remaining arguments. The control argument is described below. The other arguments, each of which must be a pointer, indicate where the corresponding converted input should be stored. The control string usually contains conversion specifications, which are used to direct interpretation of input sequences. The control string may contain blanks, tabs, or new lines, white space characters, which are ignored, ordinary characters not present, which are expected to match the next non-white space character of the input string. Conversion specifications consisting of the character present and optional assignment suppression character asterisk and optional number specifying a maximum field width and a conversion character. A conversion specification directs the conversion of the next input field. Normally the result is placed in the variable pointed to by the corresponding argument. If assignment suppression is indicated by the asterisk character, however, the input field is simply skipped. No assignment is made. An input field is defined as a string of non-white space characters. It extends either to the next white space character or until the field width is specified is exhausted. This implies that scanf will read across line boundaries to find its input, since new lines are white space. The conversion character indicates the interpretation of the input field. The corresponding argument must be a pointer, as required by the core by value semantics of C. The following conversion characters are legal. Okay, like this: D, O, X, H, C, S, F. Okay, here. The conversion character D, O, and X may be preceded by L, letter L, to indicate that a pointer to long rather than in appears in the argument list. Similarly, the conversion characters E or F may be preceded by L to indicate that a pointer to double rather than float is in the argument list. For example, the call with the input lines something. We will assign the value 25 to I, the value 5.432 to lowercase x, and the string something. Properly properly terminated by \0 to name. The three input fields may be separated by as many blanks, tabs, and new lines as desired. The call, like this, with input, like this, will assign 65 to I, assign 789.0 to X, skip over 0, 1, 2, 3, and place the string 4, 5 in name. The next call to any input routine will begin searching at the letter A. In these two examples, name is a pointer and thus must not be preceded by a ampersand. As another example, the rudimentary calculator of chapter 4 can now be written with scanf to do the input conversion. The code like this: scanf stops when it exhausts its control string, or when some input fails to match the control specification. It returns as its value the number of successful matched and assigned input items. This can be used to decide how many input items were found. On end of file EOF is returned. Note that this is different from 0, which means that the next input character does not match the first specification in the control string. The next call to scanf resumes searching immediately after the last character already returned. A final warning: the arguments to scanf must be pointers. By far, the most common error is writing instead of 7.5 in memory format conversion. The functions scanf and printf have siblings called scanf and printf, which perform the corresponding conversions but operate on a string instead of a file. The general format is printf formats the arguments in arg1, arg2, etc. according to control as before, but places the resulting string instead of on standard output. Of course, string had better to big enough to receive the result. And as an example, if name is a character array and n is an integer, then like this, create is a string of the form temp and n is in name, where n is the value of n. Scanf does the reverse conversions. It scans the string according to the format in control and places the resulting values in arg1, arg2, etc. These arguments must be pointers. The call sets n to the value of the string of digits following temp in name. Exercise 7 (2). Rewrite the desk calculator of chapter 4 using scanf and or scanf to do the input and number conversion. 7.6 File access. The programs written so far have all read the standard input and written the standard output, which we have assumed are magically predefined for a program by the local operating system. The next step in iSnapshot is to write a program that accesses a file which is not already connected to the program. One program that clearly illustrates the need for such operations is CAD, which concatenates a set of named files onto the standard output. CAD is used for printing files on the terminal and as a general purpose input collector for programs which do not have the capability of accessing files by name. For example, the command prints the contents of the files x.c and y.c on the standard output. The question is how to arrange for the named files to be read, that is, how to connect the external names, that a user thinks of to the statements which actually read the data. The rules are simple. Before it can be read or written, a file has to be opened by the standard library function fopen. Fopen takes an external name like x.c or y.c. Does some housekeeping and negotiation with the operating system, details of which needn't concern us, and returns an internal name which must be used in subsequent reads or write of the file. This internal name is actually a pointer called a file pointer to a structure which contains information about the file, such as the location of a buffer, the current character position in the buffer, whether the file is being read or written. And the like, users don't need to know the details because part of the standard ISNATION definitions obtained from Studio.H is a structure definition called file. The only declaration needed for a file pointer is exemplified by like this. This says that fp is a pointer to a file, and fopen returns a pointer to a file. Notice that file is a type name, like int, not a structure tag. It is implemented as a type div. Details of how this all works on the Unix system are given in Chapter 8. The actual call to fopen in the program is like this. Okay guys, it is time for me to have a break. Okay, here it is. See ya.